Hello, this is Mr. Huber. In this lesson, we're going to look at geometric sequences. Geometric sequence is a list of numbers, like an arithmetic sequence, only now there's a common ratio between the listing of numbers, okay, instead of a common difference. An arithmetic sequence, there was the same number being added or subtracted each time to get the next number. Now we're going to notice there's the same ratio, means the same thing that's being multiplied or divided each time to get the next number in the sequence. So if we look at number 1, we've got a listing of numbers 3, 9, 15, 21, and 27. Right here. Okay. So we want to look and see, is there a common difference or ratio that might make it arithmetic or geometric. So 3 plus 6 is 9, 9 plus 6 is 15, and we can see we can keep following that pattern. We're adding 6 each time. Okay, another way you could figure that out is take a number and subtract the number before it. So if I take 9 minus 3, I get 6. If I take 15 minus 9, I get 6. And so on. That's the common difference, right? Difference is the result when you subtract two numbers. So this is arithmetic. Okay, and it has a common difference of 6. Okay, the common difference is 6. Then we look at number 2. You might think, okay, 3 minus 1, that's 2. But then 9 minus 3 is 6. So there's not a common difference, all right? This is not arithmetic. There's not the same difference between all the numbers. So to find a common ratio, instead of subtracting, we can divide, right? Ratio is comparing one number to another, 3 to 1, 9 to 3, and so on. So if I divide all of these, 3 divided by 1 is 3. 9 divided by 3 is 3. 27 divided by 9. 81 divided by 27. Those all come out to 3. So this is geometric. It is a geometric sequence because I have a common ratio. Okay? Common ratio between any two consecutive numbers. Right? And the common ratio is 3. We saw that. We do 3 divided by 1, 9 divided by 3, and so on. We use R for common ratio, 3. D for common difference in an arithmetic, R for common ratio in a geometric sequence, and we got a common, means it has to be the same for all consecutive numbers in the sequence. The last example, number 3 here, we go from 5 to 10. So again, first we can see, is there a common difference? 10 minus 5 is 5. 20 minus 10 is 10. So there's not a common difference, so that's not going to work. So then we could look at, is there a common ratio? 10 over 5 is 2. All right, 20 over 10, that's 2. But 35 over 20 does not equal 2. So there's not a common ratio. Again, it has to be common ratio, the same for the entire sequence, not just part of it. So this would be neither. Okay, not every list of numbers is arithmetic or geometric sequence. This one's neither of those. Is there the same difference? Arithmetic. Is there the same ratio? Geometric. Neither. All right, it doesn't have to be either one of those. So now we want to look at ways we can write out geometric sequences, okay, like we did with arithmetic sequences. Okay, we have a starting value, a, or oftentimes we write it as a sub 1, okay, in a common ratio. So that listing of numbers would be whatever the starting value is times whatever the common ratio is, times whatever the common ratio is squared, times whatever the common ratio is to the third. Again, we're multiplying by the ratio each time. So if we take a times r and multiply by r again, we get a r squared. We multiply by r again, a r cubed, right? We're multiplying by r each time to get the next number in the sequence. We saw that up here with example number 2, where we did times 3, times 3, times 3. We multiply by r each time. Okay? And then we have recursive and explicit formulas and definitions we can use. A sub 1, starting value. A sub n is the value we're trying to discover and find. So if we're looking for the 25th term, this would be a sub 25. We take the number before it and multiply by the common ratio. We saw that with what we just talked about. We multiply by 3 each time. Well, we've seen we don't want to necessarily find out 50 terms to figure out the 51st one is. So we can find it directly. If we want to find term a sub 50, we take the first term and multiply by whatever the common ratio is to the power of n minus 1. If it was 50 here, then we do 50 minus 1 as our exponent. Okay? So an explicit definition will help us find some number in the sequence directly without having to figure out all the ones before it. We're going to see how we can use these things here with some examples. Right? So number 4 is, what is the 12th term of the geometric sequence? It begins 3, 12, 48. So it's telling us it's geometric. That's nice. So now we can figure out the common ratio. Okay? So I would do 12 over 3, 48 over 12. Those equal 4. That's my common ratio. So to figure out a sub 12, I take the first number in my sequence, that's 3, and I multiply that by 4 to the power 12 minus 1, n minus 1. So that's 3 times 4 to the 11th power. And we're going to need a calculator for this. It's a pretty big number. 12,582,912. You should work that out, make sure you're getting that same thing so you know you're putting yours in the calculator correctly. Okay? To find the 12th term in the sequence, we take the first term times the common ratio to the power of n minus 1. In this case, n was 12, so 12 minus 1. Okay? So you should try number 5, see what you can do to come up with the 10th term in that geometric sequence. All right, so hopefully you've paused and had a chance to try this problem out, and now we'll go through it. We first want to figure out the common ratio. So negative 6 over 2, 18 over negative 6, those come out to negative 3. Our ratio can be a negative, okay? Our ratio can be a negative. We see here it's a negative 3. Okay, we're multiplying each time by negative 3, so we should be seeing a change in signs. Positive times negative 3 is negative. Negative 6 times negative 3 is positive 18. The next number should be a negative number, and so on. Okay, and then we can use our explicit definition here to find term 10. So a sub 10, okay, that's going to be 2, the first term in our sequence, times negative 3 to the 10 minus 1. So that's 2 times negative 3 to the 9th. Make sure you're using parentheses and things correctly where you're taking negatives to powers in particular. Okay, so this will come out to negative 39,366. One thing we could look at here is that we see our first term positive, second term negative, third term positive, our fourth term should be negative. We'd see that every odd term is positive, every odd term is negative. Every even term is negative, right? Term 1 and 3 are positive, term 2 and then term 4 would be negative, so we should expect the 10th term, an even number term, should be a negative, because these are alternating each time you multiply by a negative. That's something just you can keep in mind, look and see, does it look like I have the right sign on my answer? Right? Does my answer make sense? Okay, so know how to use the explicit definition here to find certain number of terms in a sequence. All right, it's a lot of work. Let's take a little break. Take me out to the ball game break. So we're going to have some trivia about baseball. You may be aware that it's 4 balls for a walk, 3 strikes for an out for a batter. So how did that come to be, and was it always that way? It was not, okay? It's gone through a lot of changes. In 1845 was the first time a set of rules was really organized and written down. There were rules before that, but they were not organized. So in 1845, the Knickerbocker Baseball Club organized 20 rules that they used. Amongst those 20 rules, there were no walks and there were no called strikes. So the only way you could strike out was if you swung and missed 3 times. And you could stand up there for 100 pitches. If they threw 100 balls, you could just stand there. The point back in that day was for pitchers to throw balls that could be hit. They were not supposed to try to strike people out. They were supposed to throw balls that could be put in play. In fact, there was a time in baseball where batters could call for where they wanted the pitch, where they wanted it high, they wanted it low. Okay, so it's obviously evolved over the years. In 1858, they instituted a called strike, but it wasn't really called, it was a warning. If a batter didn't swing at a good pitch, he got a warning that he should start swinging. Okay. In 1863, they started calling balls for the first time, and it took 9 balls for there to be a walk. That was because, again, the pitcher could throw 50 balls if they wanted to. They just keep throwing terrible pitches, hoping eventually the batter would swing because there was no walks. There was no penalty for it. Again, this kept evolving over the years. In 1880, there started a real series of changes that happened every year or two. They started tinkering with the rules, and the lowering for the number of balls for a walk kept going down, and they eliminated the warning strike. okay, warning strike. There should be an S in front of that for strike, not trike, okay? So a warning strike. So there wasn't a warning strike anymore. It was actually called strike. So they started calling balls and strikes. And then 1889 was when it first instituted 3 strikes for an out, 4 balls for a walk, and it's been that way since. So it's been a long time, but in the beginning days, there were a lot of variations that went with that to get where we are today. All right, some more guided practice. If we're going to find the missing term in a geometric sequence, when it was arithmetic, we want to find a term in between 2, we just add them and divide by 2. Well, we can't do that here in a geometric sequence, okay? In a geometric sequence, we don't add and divide by 2. What we have to do is multiply and then take the square root, okay? So adding 2 numbers and then dividing by 2 for arithmetic. Now for a geometric, we're going to take the square root of the product, okay? The square root of the product. So this is a geometric mean. That's what we're looking for, right? The mean of these two, but it's in a geometric sequence. So a geometric mean is the square root of the product of the 2 numbers. So you multiply them and take the square root. So that's the square root of 100, which is 10. And we can see, does that seem like it might follow a pattern? Well, sure, I could divide by 2. 20 divided by 2 is 10. Divided by 2 is 5. Or if you want to look at terms of, oh, I thought it was supposed to be something you multiply by, that's multiplying by a half, or 0.5, okay? So to go from each number to the next, we're cutting it in half. We're multiplying by a half, or multiplying by 0.5, okay? Same thing. One thing you want to be aware of, we've seen geometric sequences that can change signs. So when you square root, you have to remember that when we square root, we can have the plus or minus. Okay, you'll notice I added the plus or minus sign in there. So we need to add that in over here. This could be a positive 10, or it could be a negative 10. Because our common ratio could be not just dividing by 2, but maybe dividing by negative 2. All right, so we don't know that for sure. So we have to use a plus or a minus. When you square root 10, it's plus or minus 10. Or when we square root 100, it's plus or minus 10. Okay? So now let's look at a couple last examples, okay, where we want to write the explicit formula and then find the first 5 terms. So for number 7, again, explicit formula. This is where we take a sub n equals a sub 1 times r to the n minus 1. We've done this a little bit before, so we'd have a sub n equals a sub 1 times 2 to the n minus 1. That's our explicit formula. We're not trying to find any specific term yet. We're just writing the formula. Then we can use that to find a sub 1, a sub 2, a sub 3, and so on. So to do that, all right, a sub 1 we know is 5. A sub 2, common ratio is 2, means we're going to multiply by 2, 10. A sub 3, we're going to multiply by 2, get 20. A sub 4, multiply by 2 again. And finally, a sub 5, multiply by 2, and we get 80. Those are the first 5 terms in our geometric sequence, 5, 10, 20, 40, and 80. If we wanted to find this number directly, right, we could do a sub 5 equals 5 times 2 to the 5 minus 1. That'd be 5 times 2 to the 4th, which equals 80. Okay? That's how we could find that directly. Or we saw that it's important, especially if you're going to find the 38th term. You don't want to multiply by 2 over and over and over and over and over and over again, right? You could find that term directly. So keep that in mind, and you can check it. That's a way you can see. Does it look like this is working, right? If I've got this list of numbers, then if I put a 5 in here for n, does it give me the 5th term? That way you'll know that this formula I wrote works to give us the terms in this sequence. Okay, you can check it. All right, so try number 8 out, and we'll see how you did on it. Okay, for number 8 over here, our explicit formula will be a sub n equals 60 times negative 0.5 to the n minus 1. Okay. 60 is our first term. Our common ratio is negative 0.5, and then to the n minus 1. So now if we're going to find the first 5 terms, our first term is going to be 60. Our second term is going to be negative 30. All right, our next term is going to be 15. Right, you see there's changing signs because our common ratio is negative, so it's going to alternate going from positive to negative each time we multiply by a negative. Then our fourth term is negative 7.5. And our fifth term is 3.75. Okay? So that's a sub 1. This is a sub 5. And if we wanted to check and see if this is working, we could do a sub 5 equals 60 times negative 0.5 to the 5 minus 1. That would be 60 times negative 0.5 to the fourth power. You got to make sure here with parentheses and negatives that you're taking different powers, you put those in correctly. But if you do, this will come out to 3.75. So it might be good to check and make sure you know how to enter things like this in the calculator properly and you're getting the right numbers so we can work that out if we need to go over it. Okay? So geometric sequences have a common ratio. Okay, we can use that common ratio to write an explicit definition. We can use it to find a specific number in a sequence and then make sure we know how to find geometric mean, which is square root of the product.